All right, we're here at Bear Trap Canyon. Will's behind the camera there. Beautiful snowy morning and the fog is lifted, so we're happy. Checking out these gneissic rocks. They are part of the Archean, Wyoming province, which is the basement here in southwest Montana. And these rocks have been deformed, and we're going to look today at the fabrics that formed during that deformation event here in Bear Trap Canyon. First thing I want to point out is the mineralogy of this rock, or the petrology of this rock, I should say. It's a sort of typical gray gneiss, so quartz and plagioclase forming these lighter layers, biotite and hornblende forming the darker layers. They've obviously separated out from each other to form a gneissic foliation, and that foliation is going to be our marker for the deformation events that we can see at this outcrop. In places in this rock, you'll actually find garnets, which are a hint that this rock has experienced some higher temperatures and pressures during metamorphism. So let's take a look at this part of the outcrop. Here we can see some interesting folds. We have some tight folding here with very angular fold noses there. And if we think about the axial plane of that fold, it's about the orientation of my glove here. So what we can interpret from this outcrop is that we had to have had an initial generation of foliation that was then folded in a second deformation event. In reality, this is probably part of the same progressive history of deformation, but geologists who work on ductile rocks typically will separate things out into a time series denoted by phases of deformation just to help with the interpretation of the rocks. So what I would say happened here is that we had the formation of the initial foliation. Typically, people will refer to this as S1, as schistosity 1. That foliation was then refolded, and then the axial plane becomes the orientation of the second foliation. So that would be, in this case, foliation S2. We have this tight folding, and in some places the limbs of the folds are actually isoclinal, meaning they are parallel to each other. All right, so we just walked about 5 meters down the hill, parallel to where we were just filming. And we're looking at another example of this folded foliation here. So again, we have our gneissic layering. You can actually see some sort of rusty colors in this rock. Potentially could be micro garnets, but mainly, again, this is our gray gneiss consisting of quartz, feldspar, biotite, and hornblende. Here, the fold limbs are a little bit more open. We have a concentric fold, and this would be our foliation 1 here, which is being folded during that foliation 2 generation. So S1 being folded into S2, which is parallel to my hand here. So the axial plane of those folds is going to form the second orientation of foliation, which, if you walked all around Bear Trap Canyon, would be the more common foliation orientation that you see all throughout this region. Let's walk around the corner here and check out this intrusive contact. So here we can see that we have a different rock type, and if we look over my shoulder, we'll get a better look at this when we zoom out on this outcrop, but this is actually an intrusive rock. It's a dike. The composition of this rock right here is amphibole, pyroxene, plagioclase, and hornblende. So it's a more intermediate to mafic composition than the surrounding country rock. And here we can see the intrusive contact between this dike and the country rock. And what I want to point out here, and just make sure everyone understands, is that foliation S1, schistosity 1, comes into this contact and is cut by it. But the orientation of foliation S2 is roughly parallel to the intrusive contact with the dike. So my interpretation here would be that because we don't see evidence for the dike cutting across S2, it is likely that those two things formed synchronously. And the orientation of the dike itself might actually be being controlled by the same regional tectonic stress that formed the foliation S2. So here we are in the center of this intermediate to mafic composition dike. If we take a close look at this outcrop, which we have a clip showing you that, but let's try it again here. You'll notice that there's a little bit of a reddish pink color to this rock. And if you took a hand lens to this, you would find that the composition is garnet, pyroxene, plagioclase, and hornblende. And the fact that we have that mineral assemblage for this bulk composition of an igneous rock tells us that these rocks experienced really high pressures and really high temperatures. So this is actually a granulite facies metamorphic assemblage that's preserved in the center of this dike. So when this rock crystallized, the pressure and temperature conditions were within the granulite facies. So to put some numbers on that, we're talking about really hot temperatures, more than 850 degrees Celsius, so close to the melting point of a typical granitic composition rock. We'll see some evidence for partial melting of granitic rocks at another location on this outcrop. And in terms of pressures, we're looking at pressures around 1 gigapascal. So in your homework assignment, you'll be doing some calculations to tell you how far down in the crust you'd have to be to get those types of pressures. But the take-home point is, the most important point is that these rocks were really hot and they were buried very deeply to create this metamorphic assemblage. The tectonic story for why we have this really extreme high temperature, high pressure metamorphism is that way back about 1.8 billion years ago, the Archean Wyoming province collided with the Archean Medicine Hat province as part of the coming together of Laurentia. So this was a continental collision. We imagine it must have been somewhat similar to the formation of the Appalachians and the Grenville province on the east coast of the US, or maybe the Himalayas today, which is our best modern example of a collisional origin. When you have pieces of continental crust colliding, you can bury rock very deeply. When it's buried to great depth, it also heats up and experiences extreme metamorphism like we're seeing here. So granulite facies, in some cases eclogite facies, which would be the equivalent of this, but at a lower temperature.
All right, so we are here, excuse me, we are here at the north edge of the intrusive igneous body here at the outcrop. Once again, you guys can see the darker rock. This is the intrusive igneous dike. And then we have the foliated country rock to the left here. Nice sharp contact. And what you guys might notice is a color change from the exterior of the dike closest to the country rock. It's a darker color compared to the interior of that intrusive dike. And one of the reasons for that is we're actually seeing a lack of garnet present in the exterior of the dike closest to the country rock. And an explanation for that, or an interpretation for that, is that this igneous intrusive body reached that peak granulite facies metamorphic conditions, but then subsequently retrogressing cooled, and so those areas that were along the exterior of the dike underwent that retrogressive metamorphism and lost that garnet, where it became unstable at those lower pressure and temperature conditions. But the center of the dike still preserves those higher metamorphic conditions and has that garnet in the rock itself.
Cool. So we've just walked about 15 meters further north, away from the mafic dike. We're looking at the country rock here. So this is the more typical Wyoming province composition. Granitic in composition, lots of quartz, feldspar, biotite, mica, and hornblende, like you'd find at a typical granite rock. What's interesting about this location here is that we have textural evidence for partial melting of these rocks. This is called a migmatite, M-I-G-M-A-T-I-T-E. And a migmatite is when you see the more felsic components of the rock actually melting and separating out from the more mafic residue. This is because, going back to your Earth 101 class, Bowen's reaction series, minerals with more silica in them, more felsic minerals, are going to melt at a lower temperature than the more mafic counterparts. So here in the outcrop we can see there's these zones where we just have hornblende and biotite left behind. The red in here is actually big garnets as well. This is what's called the melanosome. Melanosome meaning it's darker in color. This is the residue that didn't partially melt. The whiter portions of the rock here are mainly composed of feldspar and quartz, very silica rich. This is the portion of the rock that actually partially melted and separated out into these sort of partially molten layers. So we can imagine that when this rock was at peak pressure and temperature conditions, it was sort of a mush of partially solid, partially molten rock. And when it crystallizes, we call this a migmatite. The garnets here are clustering in the melanosome because the melanosome is going to be more iron and magnesium rich. One of the key building blocks of a garnet is iron, especially for these type of garnets, which are likely almandine garnets. So you find garnets here in the melanosome, not as common in the leucosome. The timing of this partial melting is probably pretty similar to the timing in which the dike achieved that granulite facies metamorphism, its peak pressure and temperature conditions. And the fact that that dike intruded around that time tells me that all of these rocks were really hot, right? We have igneous activity going on. The country rock was also very hot because it was deeply buried. Things were hot, rocks were deforming and flowing ductily over geologic timescales, and this all relates back to that history of the collision between two pieces of continental crust. Okay, so I got Will to climb up on the outcrop here. He's going to act as our scale and our tour guide for this outcrop. Some interesting folding happening here. Again, we can see the foliation S1, that first generation, being refolded into S2, which is going to be parallel to the axial planes of these folds, and also parallel to the layering you can see on the rock outside of the zone of folding. You can also see a really nice boudin down there to the left of Will, so a more mafic enclave there, and it has been stretched apart. There was likely an entire complete layer of that darker material, much like you see in the folds. And what happened was it was basically compressed in one direction and stretched the other direction, and it's separated out into these pods. And once we zoom out and look at the full outcrop, we'll notice that the Granulite Dike was actually stretched in a very similar manner and is what is a much larger boudin pod. So these folds up here, we would call them Z folds because of their shape. If we rotated this foliation back to horizontal, it would tell us that there's a top to the south sense of shear on this outcrop. The orientations of foliation have been a little bit messed up by the younger mountain building history associated with the Laramide event. There's a brittle fault on the north side of Bear Trap Canyon, which actually uplifted these rocks. And these ductile structures formed well in advance of that deformation history, but they were all rotated by that younger brittle deformation. All right, I think that's it. Thanks, Will.